My name is Sarah, and today we'll be talking about quantum supremacy. Okay, so before we go over everything, just wanted to talk about the objectives and what I hope that we all will be able to take from today's lecture. So by the end of today's lecture, we should be able to define quantum supremacy. We should be able to understand the basic concepts of quantum mechanics and how it works. We also should be able to brainstorm different areas in which quantum mechanics is currently being used and currently has an impact. And we should be able to differentiate between characteristics of a quantum computer versus a classical computer, and also discuss some potential concerns. So, just for curiosity, is there anyone in here who has extensive knowledge in quantum? Maybe you don't count. Is there anyone else in here? No? Okay, so I guess it will be a very rewarding lecture for all of us. So let's get into quantum mechanics. So, according to Oxford Dictionary, quantum mechanics is the branch of mechanics that deals with the mathematical description of the motion and interaction of subatomic particles, incorporating the concepts of quantization of energy, wave-particle duality, the uncertainty principle, and the correspondence principle. So basically, put simply, it is the discipline of physics that describes the phenomena in nature using the smallest units, so atomic and subatomic units. So why is quantum mechanics so important? Why are we talking about it right now? Quantum mechanics is important because it plays a fundamental role in explaining how the world works, not only in terms of microscopic systems, but in all physical systems, regardless of their size. And it tells us a lot about the structure of reality, and it allows us to explain the phenomena that can't really be explained with classical physics, such as single particle interference and entanglement, and superposition, which we'll get into later. Quantum mechanics has some importance in technology, as we already know. It is needed to design optical and electronical components, which often take advantage of certain quantum mechanical effects. And is also important for the theory of computation, which we'll talk about later. Okay, so what currently uses quantum mechanics? There are certain things that we know and we use in our day-to-day lives that use the fundamental components of quantum mechanics, like MRIs, lasers and telecommunications, atomic clocks and navigation systems, and of course computers and smartphones. So first up, MRIs. MRI machines, they use NMR. If anyone in here took OChem, then you already know about NMRs. But basically, it works by flipping the spins in the nuclei of hydrogen atoms, and the arrangement of the magnetic fields allows the doctors to measure the concentration of hydrogen in the body, and it allows them to distinguish between the different types of tissues, which you can't really tell in regular X-ray machines. So with lasers, the key physics in the laser is actually coming from a paper written by Einstein in 1917, which talks about the statistics of photons and the interactions with atoms. So he introduced the idea of stimulated emission, where an atom in a high energy state encounters a photon of light with the right wavelength, and is also induced to emit a second photon of the same identical, the same wavelength as the first one. So the process is partially responsible for light amplification by stimulated emission of radiation, also known as a laser. So, fun fact, a laser is actually an acronym, I didn't know that. So anyways, quantum mechanics is also used in fiber optic telecommunications. The fibers actually have lasers going through them, so that is when we get the quantum mechanical part of telecommunications. So anytime you're making a phone call with a landline, I don't know if anyone still does that, but if you're making a phone call with a landline, or you go to the grocery store and you're scanning your items, they are indirectly using quantum physics. Okay, so atomic clocks and a GPS system. one of the most common uses of our phones is trying to figure out where we need to go, navigation systems. So basically, the GPS uses quantum mechanics, and the receiver picks up the signal from multiple atomic clocks at the same time to determine your distance from those satellites. And the mechanism relies on the constant speed of light to convert time to distance. So light moves at about a foot per nanosecond, so it's very important that the timing of the satellite is very, very precise. So finally, the computer. A computer is an electronic machine that processes information, so it's an information processor. It takes in raw information as data, and it stores it until it's ready to work on it, and then it chews on it, works on it for a bit, and then it releases some results for us to use. Computers use binary numbers, so therefore binary digits instead of decimal digits. So with that being said, it could either be a 0 or a 1. We'll get into that later. I don't know, I hope it makes sense, but there's a video later that can explain it a little bit better. So the word bit comes from binary digits, so the B from binary and it together is bit. And basically bits are really small, so we don't really work with bits. We work with an arrangement of bits, an arrangement of 8. And 8 bits together makes a byte, so that's where we get gigabytes, megabytes, and all that fun stuff. Okay, so the star of the show today, the quantum computer. Quantum computers differ from classical computers because they're not limited to 2 states. With a classical computer, like we mentioned before, they use binary digits, so it can either be a 0 or 1. But with quantum computers, we still have binary digits, but they can coexist at the same time. So it can be a 0 and a 1 at the same time. I know it doesn't make sense, but we'll explain more. Qubits represents atoms, ions, photons, or electrons, and their respective control devices, and that are working together to act as computer memory or to act as a processor. So because a quantum computer contains these multiple states at the same time, it is so much more powerful than a classical computer. And it can solve problems that are impossible or would take a regular computer a lot of time to do. So today, we produce about 2.5 exabytes of data, and that is equivalent to 5 million laptops running at their highest potential at the same time. So we need quantum computers because they are capable of processing that amount of information. So this is just showing the differences between the classical computer and the quantum computer, like we mentioned before. So it's very important to remember classical computers use bits, quantum computers use qubits. So it can be 0 and 1 at the same time. And I have a video that should explain it a little bit better.
Quantum physics, one of the most successful theories of modern science, describes the way our world works at the most fundamental level. Quantum computing has become one of the leading applications of quantum physics. Quantum computers have the potential to solve some of the world's most complex problems that are beyond the reach of even today's most powerful supercomputers. Quantum computers are not going to replace classical computers, but their radically different way of operating enables them to perform calculations that classical computing cannot. Let's see how they differ. Classical computers encode information in bits, and each bit can represent a 0 or a 1. These zeros and ones act as on-off switches that ultimately translate into compute functions. To perform a simple calculation, like solving a maze, a classical computer would test each possible route one at a time to find the correct one. Just as classical computers have bits, quantum computers have qubits. Qubits, however, make use of 2 key principles of quantum physics: superposition and entanglement. Superposition means that each qubit can represent a 0, a 1, or both at the same time. And entanglement happens when 2 qubits in a superposition are correlated with one another, meaning the state of 1 Whether it's a 0, a 1, or both depends on the state of another. Using these two principles, qubits can act as a much more sophisticated version of switches, helping quantum computers solve difficult problems that are virtually impossible using classical computers. To illustrate how this makes quantum computers more powerful, let's look at some numbers. Take a classical n-bit computer, with n representing the number of bits. It can represent and examine only one system state at a time. An n-qubit computer, however, would have the power to represent 2 to the power of n system states and perform parallel operations on all those states at once. This means that every time you add just one more qubit to a quantum computer, the number of states it can represent and examine doubles. So a 50-qubit quantum machine could examine 2 to the power of 50 states at once. This exponential increase in power, together with the entanglement of qubits, is what allows quantum computers to solve certain problems so much more efficiently. While a classical computer solves a problem like the maze by testing each possible route one at a time, a quantum computer uses its entangled quantum states to find the correct route quicker, with far fewer calculations. Think of it this way. Technologies that currently run on classical computers can expertly find patterns and insights buried in vast amounts of existing data. But quantum computers will deliver solutions where patterns cannot be seen because sufficient data does not exist, or the possibilities for discovering an optimal answer are too enormous to ever be processed by a classical computer. Quantum computers could lead to the discovery of new medicines and materials by helping us untangle the complexities of molecular and chemical interactions. They can help the financial services industry make better investments by finding new ways to model financial data and isolate key global risk factors. They could even transform supply chain and logistics by finding the optimal routes across global systems, like optimizing fleet operations for deliveries during the holiday season. Quantum computing won't replace our everyday computers and smartphones, but its ability to solve complex problems will open up a new universe of information, transforming our view of the world and the way we navigate it.
Okay. So I hope that video explained it a little bit better, just the concept of superposition and entanglement and how a quantum computer works. So onto quantum supremacy. Quantum supremacy can be defined as the goal of demonstrating that a programmable quantum device can solve a problem that a classical computer practically cannot, or it can solve a problem faster than a classical computer can. Now, ever since the issue of quantum supremacy and quantum computers came to be, there has been what has been called the quantum race. So basically, there's been a lot of different efforts from different parts of the world, and they're all basically trying to be the first to come up with a quantum computer that can achieve quantum supremacy. So we can see that there's a lot of efforts in Europe and in the US as well, but it can be said that the quantum race isn't really about nations competing with each other. It's about the entities, like the big enterprises like IBM and Google and Intel and Microsoft, and they would be right. Because a couple of weeks ago, Google came out with their paper claiming that they achieved quantum supremacy with their Sycamore processor. There was a lot of noise about this because IBM stated that they were cheating. So basically what they said was they achieved quantum supremacy by creating a programmable task for the quantum computer and the classical computer to run at the same time. And of course their quantum computer finished the task, but the classical computer did not, and they claim that it would have taken the computer 10,000 years to complete something that the quantum computer finished in 200 seconds. Now, IBM's claim was that they rigged it so that the quantum computer would excel in the task and the classical computer would fail. Well, Google people said they achieved quantum supremacy, so let's see. Let's find out what they said.
The tantalizing promise of quantum computers is that they can do certain tasks exponentially faster than classical machines. And the quantum supremacy experiment is proof that this is indeed the case.
The word quantum computer is a little bit misleading because it sounds like a computer. And when people think of computer, they think of a phone or a laptop. The truth is the phone and the laptop and even a very powerful supercomputer all operate according to the same fundamental rules. And a quantum computer is fundamentally different.
The classical bit stores information as a 0 or 1, and a quantum bit can be both 0 and 1 at the same time. If you have 2 quantum bits, then there are 4 possible states that you can put in superposition. With 3 qubits, it's 8, 4 qubits, it's 16, but grows exponentially.
The nice thing about quantum supremacy is that it is a very well-defined engineering milestone.
In a nutshell, what we're trying to do is we're trying to show that experimental quantum computers can surpass the best supercomputers in the world.
To actually demonstrate quantum supremacy, we have these 3 steps. First, pick a circuit. Second, run it on the quantum computer. Third, simulate what the quantum computer is doing on a classical computer. And we gradually increase the complexity of that circuit. And at some point, it becomes completely impossible for the classical computer to keep up. Then we say we've achieved quantum supremacy.
We started building together the quantum chips to do this experiment. And then the evolution of the devices were more and more qubits and more complexity. It's very much an iterative process.
A lot of the work that we put in was not just these chips, but is also the infrastructure that you need to drive those chips. The cryostats that we install them in, all of the control electronics, software, all of this stuff is needed, and it all has to be developed.
When the experiment started, we were getting data from the experimentalists. We saw initially a beautiful straight line corresponding to our predictions.
Then, right before we hit supremacy, it dropped much faster and it fell below the threshold where it needed to be.
And there's nothing we can do because we don't know how to analyze past that. So everyone's like, oh, we're screwed because it's getting really, really bad at large number of qubits.
It's like, well, maybe there's some really complex interaction between all the qubits.
It turned out that the reason was rather benign. We calibrated it a little bit better and this problem disappeared.
So there wasn't like we did it.
I think we crossed it, and then it wasn't clear that we crossed it, so we crossed it a little bit further.
It took me like a day to realize, hold on, this is actually experimental data. It's kind of amazing to see, how well the theory works.
The processor that achieved quantum supremacy is called the Sycamore processor.
And it's parallel processing 2 to the 53 states, which is 10 million billion. And thus that enormous amount of parallel processing is what gives it the power.
When we run a small chunks of the computation, it's the largest supercomputer in the world. Our estimate is that it will take thousands of years to complete the full computation.
Technologies are born this way. Let's say the space age started with a satellite orbiting Earth, and it was not doing much, it was just beeping.
The big technical achievement of quantum supremacy was really dependent on all this young talent who's kind of taken this and gotten it to work at a very technologically capable level.
We have reached a new computational capability. There are certain computations, the only place in the world where you can compute those things is here in our data center at Google Santa Barbara.
For the first time, we're showing that we can solve a problem that was just infeasible to do on the biggest computers ever made by civilization.
And what's exciting is now we're ready to turn this over to the world and say, let's figure out what we can do with this.
The thing that excites me most is building a useful quantum computer. When we can give a researcher a tool that is unlike any other and say, great, figure out something cool to do with it. Mankind is pretty good at that.
Okay, so what does this mean for us? Now that we have we are capable of producing a computer that can process so much information in so little time. What does this mean for us? Now, like they mentioned before, a quantum computer is not a computer that we'll be able to carry around with us like we carry a laptop, and it's not going to be used for that purpose. So they're going to use it for different things, a lot of more sophisticated things. It's not something that we can use to check our emails or make a banking transaction. But it is capable of destroying, well not destroying, but decoding an encryption that we find is very, very eloquent. So our computers are not able to decode that kind of information, but a quantum computer can. And with that being said, it can basically open all our emails, open our transactions, open anything that we want to keep secret. So what does that mean for people who will never be able to keep our hands on a quantum computer? What does that mean for us? People who will always be using a regular computer, where do we see this affecting our everyday life? Knowing that there could be an agency or a secret group that took the quantum computer, or a place that got that information and it's not trusted, right? So if they have that information and they're able of hacking and going into our stuff, what does that mean for us? How do we prepare to live in a world where that information that can be used by anyone? I'm throwing this question out to everyone, by the way. Yes.
I know there's been research into developing technology that's resistant to quantum computing and stuff that actually prevents it from hacking into those or decoding a lot of those messages and all that information. But I don't think it's super advanced enough yet. But that being said, I mean, quantum supremacy hasn't really become the norm, so I think they will probably be built in par with one another. But I think that's probably the only way that we could really sort of do that, and in terms of and then just regulation and other things, but that's also difficult to do. So I don't think there's any clear-cut good answer for this situation.
Because there's a lot of underground companies that are trying to create their own version of the quantum computer. So if they can have access to that information right now and create their own, there really isn't a clear-cut way to have our own resistance to this, right? I don't know if there's anyone else wants to add.
Well, quantum encryption will be a thing, so that right now we're using different kinds of encryption, and quantum computers will be able to crack that. But there will be new kinds of encryption. So you'll have two parts of your life, probably, part that was encrypted the old-fashioned way, and now that can be easily broken if somebody has incentive to do it, right? If you're not much of a target, if you're not a celebrity or whatever, maybe nobody will ever crack your emails from the past, even though they could have. But there'll be a new kind of encryption based on quantum, and so it will be possible to keep secrets. It's just in a different way. So when television began, it was very, very expensive, and there were less than 100 of them, right? And then rapidly it became something that sort of everybody had. And so that will also happen here. I know when you look at the cryostat part of this and learn how very cold the inside is and so on, you're thinking, I'm never going to have access to that. But that doesn't mean you couldn't have remote access to it, that you couldn't be connected to it in some way. It's just you can't carry around the actual quantum computer in your backpack. But yeah, so it isn't I mean, one way to think about the future that's almost always flawed is humanity running aground. You know, suddenly humanity's stuck. There's no solution, we're stuck. Well, generally that just means that you haven't thought through the problem enough, because, humanity is good at finding new ways to do things and, adapting to new circumstances. So, and I think the same applies here. So, and the lack of privacy has been coming for a long time. I mean, even if this didn't happen, I mean, think of nanotech and the idea of assembling surveillance cameras from dust that you can't even see, right? So you walk into a room and unbeknownst to you, there's this organized dust that's taking pictures of everything, right? So there are two ways to hide things. One is to make it difficult for people to get there. The other way is to make it so obscure that nobody even knows it's there, or they don't have a clue that they would even want to look there, right? So and that to some extent will still work. If the target cannot be identified, even though it'd be very valuable if somebody found this thing, but if nobody knows that it exists, they have no idea where it is, they have no idea who knows where it is, you can think of many, many layers of that sort of, privacy through obscurity. And so that will also work in some sense in the future. Whatever system is set up, there'll be some people who are somehow outside of that system. It may not be very much fun to be outside the system, but you can still do it, right? So, yeah.
Okay. Well, apart from privacy, what other issues, concerns do you think could rise up from quantum computing being a big thing in the future? Yes.
I guess accessibility, because since it is, when new technologies emerge, usually there's sort of a period where it's super expensive, like with televisions where people can afford it, and it takes a long time before people actually can get access to it. So realistically, what's probably going to happen if this occurs is it's going to be like major corporations, or it's going to be big countries, big powerful countries like the United States, like China. So there's a whole lot of other issues that emerge with that in terms of why do those countries get access whereas other countries don't, and will this just sort of further the divide between the developed countries that have access to all this technology and all these resources and the countries that are still have really weak infrastructure and will never probably get to that point. It just kind of widens that gap and allows the powerful countries and the powerful actors to just get even more powerful.
Yeah, and the other side of that is, think of now the grandest aspiration you've ever thought of, like the biggest deal kind of thing you ever thought of, maybe you doing or somebody else doing. And there were always limits on that based on what's possible, right? So quantum computing is going to make many things possible that were just absolutely impossible before. So it means you can dream things, you can aspire to things, like think of even simple concepts like world peace, or, making the whole earth a green and happy place for all beings, right? I mean, both of those things are things that everybody would want, but most of us think, well, that's crazy, because think about this and that, so you can imagine that a kind of really utopian world that would be a lot of fun to live in. We used to think about that and fantasize, but we always knew it was absolutely impossible. So this kind of raises the possibility that maybe it could happen. So I mean, that's another way to think about
Any other questions? No? Well, I'm done, that's it. Thank you.
Okay, well, that was really great. Thank you. And I think not every presentation